All right, so today we're going to be starting chapter 27, which is the beginning of our unit on magnetism. Today we're just going to have a small introduction to magnetism, magnetic flux, magnetic forces, and then in chapter 28 we'll look at the how to calculate magnetic fields. So magnets have a north pole and a south pole, and just like in electricity, opposite poles attract. So just like our case for electric charges, opposite poles of a magnet attract. So all magnets are made up of a north and a south pole. We call them north and south instead of positive and negative for magnetism. So the opposite poles attract, so our north and our south pole will attract, and our like poles will repel. So north and north will repel, south and south will repel. Now the most famous example of a magnet that everyone knows is the Earth. So the Earth has a magnetic field around it that shields us from the radiation from space. So obviously in space there's very harmful radiation, and our magnetic field actually shields us from this, otherwise we would not be able to live here. So this actually is what causes the northern lights. It's basically just these dangerous particles interacting with our magnetic field as they enter the atmosphere. So that's why the northern lights are called the northern lights, is because it happens at very, very northern regions where basically the magnetic field is coming into the Earth. So our magnetic field looks like this. It comes in at the poles, comes down here, comes back out at the South Pole. And now one unfortunate thing is that the geographic North Pole is actually our magnetic South Pole, and the geographic South Pole is our magnetic North Pole. So they're named opposite what they really are physically, but that's okay. And these poles actually switch every like 10,000 or 100,000 years. The poles of our magnetic field actually reverse. So maybe in like a couple thousand years, the North Pole will be the true North Pole and the South Pole will be the true South Pole. So here I have drawn some magnetic field lines. So just like with the electric field, we can have magnetic field lines. So a couple things about magnetic field lines. They show the direction that, let's say if you put a compass in a magnetic field, the magnetic field lines will show you what direction that compass would point in. So if we have a magnetic field going like this, where our magnetic field lines are like this, a compass, if you put a compass, it would point in that same direction. The north pole of that compass would point in the direction of your magnetic field lines. So that's what they have drawn here. And this little red here just means that it's the north pole of the compass. So the north pole of this compass will point along the direction of the magnetic field lines and point you to the geographic North Pole. And now if you were taking an in-person lab, you would actually be doing this in lab, where you would have compasses and you would put them in a magnetic field and see which way the compass points, but oh well. So just like for electric field lines, the density of magnetic field lines corresponds to the strength of that magnetic field. So if we have a magnetic field where the lines are super dense compared to a magnetic field like this magnetic field is stronger in this region than this magnetic field in this region. So the same as the electric field lines in that case. And it's, again, the same as in the case of the electric field, the direction of the magnetic field, the vector field, is tangent to the field lines at every point. So when we have a magnetic field line, let's say that goes like this, that means that the magnetic field, the vector field, is tangent at every point to that field line. And now one thing that's very different about magnetic fields, which we're going to talk more about in a second, compared to the electric field, is that magnetic field lines never start or end on a charge or a point. We will only ever see magnetic field lines that loop back on themselves, or they start at infinity and end at infinity. Okay, so now let's talk about magnetic flux a little bit. So magnetic flux is defined in the exact same way as electric flux. This is here the flux over an open surface. So this is very careful. We have to be very careful with our open versus closed surfaces. So this is just the magnetic flux through some open surface. So again, just like in the case of the electric field, if I have some open surface like a sheet like this, and then I have some magnetic field going through it, the flux of the magnetic field going through that surface will just be the integral of B dotted into the area element, or for a constant field, just B dot A. So just like for the case of the electric field. And this is because the magnetic field is a vector field just like the electric field, and you can calculate the flux of any vector field. So now, to get more into the physics, since the magnetic field is a vector field, we can write a Gauss's law for the magnetic field just like we did for the electric field. However, there's a slight difference. So remember, for the electric field, we had Gauss's law was like this, where the electric field, the flux of some electric field in a closed surface was equal to the enclosed charge in that surface, right? But now for the case of the magnetic field, we don't have that Q enclosed anymore, and it's actually just equal to 0. So this equation tells us that the flux, the magnetic flux, out of any closed surface at all, will always be 0. And this equation implies that there are no magnetic monopoles. So what is a monopole? A monopole is just a single charge, like when we just had our point charges Q. Those are monopoles. So something like, our just positive point charge Q was a monopole, and then when we had those positive and negative charges together, this was a dipole. So what that equation tells us is that you will never see a magnetic charge just by itself. So this does not exist in magnetism. We have no magnetic monopoles. Magnetic charges only appear as dipoles, which is why if you have a bar magnet with a north and south pole, and let's say you break this magnet into two smaller magnets, so you just break it in half, it'll just break into another north and south pole. So you can never get magnetic monopoles just by themselves. You'll never see just a north pole or just a south pole. It will always be that dipole configuration. Now, of course, this is just according to our current understanding. We've certainly had experiments that have searched for magnetic monopoles. We've never found any. We don't think they exist. If we did find some, that would really be quite a surprise and really change a lot of things in how we understand modern physics, but we're pretty sure that no magnetic monopoles exist. So this actually leads us to our third Maxwell's equation. So this is Maxwell's third equation in integral form, and then this is in differential form. So like I said, in integral form, it's just saying that the flux, the magnetic flux out of any closed surface is always 0. So however many magnetic field lines you have coming into a surface, you have that many going back out. Then this equation just tells us that the divergence of a magnetic field is always 0. So for example, if we have our north and south pole of a magnet, our magnetic field will look like this. So our arrows will come out of the north pole and go back into the south pole, which means that if we write any closed surface, let's just draw a closed surface around our magnet, we can see that we have, let's say, two field lines coming out of the magnet, and we have two field lines going back in. And then if we think of it in terms of the divergence, this just tells us that we will never have a magnetic field that looks like this. So we'll never have a magnetic field that looks like sort of the electric field of a point charge. That sort of field will never exist for a magnetic field. So this will never happen. But we can have any kind of field that has no divergence, that has no source or no sink. That field is fine. So a constant field like this is okay. A rotating field, which we'll see in our next lecture really. So if we have a field that sort of is like this, this field has no divergence. And then we'll see some other fields that are all right in our chapter 28 lectures. So today we're going to be working with uniform magnetic fields though. So just magnetic fields that look like this. So now let's talk about what actually produces a magnetic field. So magnetic fields are very interesting because they're only caused by moving charges. So if your charge is just sitting there, it cannot produce a magnetic field. Similarly, magnetic fields are only felt or magnetic forces are only felt by moving charges. So when you have stationary charges, they cannot feel nor produce magnetic fields. Now, you might think that this isn't true because a magnet has a magnetic field and it's not moving, but we'll talk about that a little bit more in our next lecture. Really, there are little charges in the magnet that are moving, sort of. But we'll talk about that in our next lecture and see why, even though the magnet isn't moving, the charges are. So magnetic fields that we'll be studying are created by moving point charges. So if your point charge has some velocity v, so let's say we get a little electron and he's moving with some velocity v, this will create a magnetic field. And also current will produce a magnetic field. Since current is just moving charges, a current will produce a magnetic field. Now, one very interesting implication of this is that you can sort of think of magnetism as a relativistic effect. So remember, we said that electromagnetism is one force, obviously. The electric and magnetic fields are actually the same force. So even though we think of them as two different forces, they're really the same thing. So what that means is that in some reference frames, what you observe as an electric field will look like a magnetic field in another reference frame. So if you're sitting still and you're just viewing stationary static charges, you'll see an electric field and you'll see only electric forces. But if you start moving, it will look like those charges are moving to you, and now it will look like a magnetic field and magnetic forces. So again, we're going to talk more about that later in our next lectures and see how that's possible. But remember, the electric and magnetic field are not really two different things. They're sort of just two sides of the same coin, depending on how you look at it. So let's talk a little bit about magnetic forces now. So like I said, magnetic forces are only felt by moving charges. If you put an electron in a magnetic field and it just sits there, it won't feel any force. But if it has a velocity, if it starts moving, then it will feel that magnetic force. So we call this the Lorentz Force Law. This is the magnetic portion. So the Lorentz Force Law says that the magnetic force on a particle, a moving particle, is given by the cross product of the charge of that particle times its velocity, and then the cross product of that with the magnetic field. So here we have the charge of the particle, so that can either be positive or negative if we're looking at an electron or a proton, and then the velocity is a vector, obviously, so that will be in some direction. And then we take the cross product of that with the magnetic field. And the magnetic field is measured in Teslas, which we denote by T. Now, there are some very interesting implications of this, which we'll talk about in a second, but let's just first review the right-hand rule. So what this Lorentz Force Law says, so the force is given by QV cross B. So if I have a coordinate system here, so let's say this is X, Y, and Z. What this tells us is that if my magnetic field, let's say, is in the X direction, and I shoot some particle into that magnetic field that has a velocity V in the Y direction, that means that the force it feels is actually going to be in the Z direction. So then our force will be in the Z direction. So whenever we calculate the magnetic force on a particle, we're going to have to use the right-hand rule or do a cross product. So just a reminder, a quick cross product trick is this little circle here. So I hat cross J hat will give us K hat, J hat cross K hat will give you I hat, K hat cross I hat will give you J hat, and then if you move in the opposite direction of the circle, it'll just introduce a negative sign. So J hat cross I hat will give you negative K hat, I hat cross K hat will give you negative J hat, and so on. And then I went through how to do the cross product of like a full 3-component vector by 3-component vector in one of my previous lectures. I forget exactly which one, but I will link it. I will write it either here or link it in the description so you can go back and watch that. Okay, and then another very important thing to remember about the right-hand rule is that it's not commutative. So this is a super easy mistake to make. Remember, your cross product is not commutative. It's actually anti-commutative, which means that A cross B is equal to negative B cross A. So you have to be very, very careful that you're actually taking the cross product of V and then B. If you do them backwards, if you do B cross V, you'll introduce an extra negative sign there, and then obviously your answer will be wrong. So it's very important to make sure that you're doing those vectors, taking that cross product in the correct direction. So the important implication of this is that magnetic fields can't do any work, right? Because to do work is F dot D. But in the case of the magnetic field, so the displacement will always be in the same direction as V, right? Because you can't be moving in a direction that you don't have velocity in. So that means for the magnetic field, F dot D will always be 0 because in order to have a non-zero force, V and B have to be perpendicular, which means F will be perpendicular to both of them. So magnetic forces never do any work, and we might get to some examples where it looks like the magnetic force is doing work, but actually it's just a hidden electric force is doing work. So magnetic forces don't do any work. If you ever see a problem that says how much work does the magnetic field do in this situation, it is always 0 no matter what. Magnetic forces can never do any work. Okay, now let's look at the full Lorentz Force Law. So the total force on a moving charge that takes into account both the electric and magnetic fields is given by this Lorentz Force Law. So we have the electric portion, which we've seen already. So this is the electric force. And then this is obviously the magnetic force. So the electric force will always be either parallel or anti-parallel to the electric field, whereas the magnetic force will always be perpendicular to both the magnetic field and the velocity that your charged particle is moving. All right, so let's do an example with this. So a beam of protons moves at 3 × 10⁵ meters per second through a uniform magnetic field of 2 teslas. The magnetic field is directed along the positive z-axis, and the velocity of the proton beam is in the xz plane at 30 degrees to the z-axis. So let's draw this. So let's just draw the x and z plane, which means the y plane is in this direction, but we don't need it. Okay, so we have a uniform magnetic field that is in the positive z-axis. So we'll draw that this way. And then we have the velocity of the proton beam is in the xz plane at 30 degrees to the positive z-axis. So that means the proton beam is sort of like this, where this is 30 degrees, that angle there. Okay, so we want to find the magnetic force on the proton. So I actually meant to write just the magnitude here. So we want to just find the magnitude of this magnetic force on a proton in this proton beam. So, and a proton beam just means a collection of protons moving in some direction. So, all right, we have F is equal to QV cross B. Okay, so since this is a cross product, we can write this just as the sign between the angles, so QVB sine theta. And in this case, the angle between our velocity and our magnetic field is 30 degrees. So we can just write that as QVB sine of 30. So the charge is a positive 1.6 times 10 to the negative 19, since it's a proton we're looking at. The velocity was 3 times 10 to the 5th meters per second. The magnetic field was 2 Tesla, and then we had sine of 30, which is 1/2. So obviously our 2 and our 1/2 cancels, and we end up just multiplying out these two numbers. So that gives us 4.8 times 10 to the negative 14 newtons. Okay, so that's this problem. Now, if we, let's say we didn't want to just find the magnitude, we wanted to instead find the full force, we would have to do the cross product. So if that was the case, let's just rewrite here. We have Z x, and then our velocity is here, which is 30 degrees. So what we could do is we could write our velocity as a vector. So our velocity would have, let's break it up into components. So that's 30, this is 60 over here. So we could write our velocity as a positive v cosine 60 degrees, since we could just take the x component of this triangle here. Cosine of 60, and then it has no component in the y direction, and then it has just a component in the z direction, which would be the sine of 60 here. So we have plus v sine 60 in the z direction. And then the same thing for the B field. It only has a component in the z direction, so it would just be 2 Teslas in the z hat direction. And now we can just take the cross product of these two vectors. So we'll have q times v of cosine 60 in the x hat plus v sine 60 in the z hat, and then cross that into 2 Tesla in the z hat. And now we can sort of make this a little bit easier, because if we look at it in components, we have an x hat crossed into a z hat. So if we look at our little I hat, j hat, k hat circle here, x hat crossed into z hat, we go backwards, so that gives us a negative j hat. So we'll get negative qv cosine 60 times that 2 in the j hat direction, or the y hat. And then z hat cross z hat is 0, because two vectors crossed into each other is just 0. So we actually get a slightly simpler expression here. So then we just end up with negative 1.6 times 10 to the negative 19. The velocity was 3 times 10 to the 5th. And then we had cosine 60, which is also 1/2. And then we had times 2. So you can see the 1/2 and the 2 cancel out. You're left with, again, just this number times this number. So we end up with the exact same, the same number here, 4.8 times 10 to the negative 14. But we have a negative and a j hat, since we found the full force using a cross product. So that's if we wanted to find the full force on that. And you could kind of tell, from the setup, since we have a velocity that's in the x and the z direction, and the magnetic field is in the z direction, that means our x component, the perpendicular component of our velocity to our magnetic field, is going to be picked out in that cross product, and we'll end up with something like x cross z, which gives us negative y. Okay, so now let's go on to cyclotron motion. So for a cyclotron is basically just a type of particle accelerator. And what you do is you have a magnetic field that is uniform and in some direction. So here we have a magnetic field that's into the page. So these little x's, when you see an x like this for a magnetic field, that means it's into the page. So we have a magnetic field going into the page. Let's say we shoot a particle into this magnetic field like this. So let's say it shoots in with a velocity that's perpendicular to the magnetic field here. What force will it feel? Well, we have to use our right-hand rule. So we'll use F is equal to QV cross B. And let's say it's a positive charge, so we don't have to worry about any negative signs. So if we use our right-hand rule, the velocity comes in and it's going to the right. So we point our hand in the direction of the velocity. We point then our fingers in the direction of the magnetic field, and our thumb points in the direction of the force. So if you point your hand in the direction of the velocity, turn your hand so that the fingers point in the direction of the magnetic field, which is into the page, you'll see your force is now going up. So as it comes into this magnetic field, our positive charge feels an upward force. So it starts moving upward, right? Its path gets deviated a little bit and it starts moving upward. So now you can see that as it moves up a little bit, the direction of the force now changes because its velocity has changed. So if you do the right-hand rule again here, you'll see that your force is directed inward a bit. And then if it moves, now it's going to move up here, and you're going to see that its velocity is directed upward. And if its velocity is directed upward, point your hand, turn your fingers in the direction of the magnetic field. Your thumb will now be pointing to the left. So now it feels a completely leftward force. And every time it moves a little bit, the force will change direction because its velocity is changing direction. So it will end up tracing out a circle, and it will just keep going in this circle because, every time it gets back to the same point, the force is going to change and it will keep it moving in a circle. So this is called cyclotron motion because your charged particle is moving in a circle in a uniform magnetic field. Now we're going to have to use a little bit of uniform circular motion from Physics 7c here to figure out what is the radius of this circle. So we want to know what radius circle will a particle of some charge and some mass and some velocity move in. So let's use our Lorentz Force Law. Now we know that F is also equal to ma, right? So we know the force will be equal to qv cross b, and we also know that the force will be equal to the mass times the acceleration. And think back to circular motion. When you have an object moving in uniform circular motion, that means there's an acceleration acting on it to keep it moving in that circular motion. So let's set these two things equal to each other. So we have qvb is equal to ma, and I could ignore the cross product here because when v and b are perfectly perpendicular, that means that the sign between them is 90 and sine of 90 is just 1. So I can just write it as qvb equals ma. Now, from circular motion, we know that a particle moving in uniform circular motion, the acceleration will be v squared over r. So I'm going to replace that acceleration with v squared over r. So I get qvb is equal to mv squared over r, where r is the radius of the circle it traces out now. So I can see that this v and this v will cancel. So I'm left with qb is equal to mv over r. And if I want to get r by itself, I can just rewrite this as r is equal to mv over qb. So this will be the radius of this circle that some particle will trace out. So this is called our cyclotron radius, and it's given by the mass of the particle times the velocity divided by the charge of the particle times the magnetic field. Now here, these are all just magnitudes, so this is just the speed really, and this is just the magnitude of the charge because we can't get a negative radius. The only time that the signs will matter is initially in the problem when you're doing that right-hand rule to figure out what direction it will spin in. Let's say, will it move upwards or will it actually move downwards and start to spin? You'd have to use the right-hand rule there, but the actual radius of the circular motion just depends on the magnitudes of those quantities. So we'll do examples like that where we do the right-hand rule and figure out what direction it spins in a minute and in our next lecture. So now what are cyclotrons used for? Well, they're used a lot actually in medical physics. So when you have to make radioactive isotopes of certain elements, they use cyclotrons to make these isotopes. So for example, some medical procedures, you have to drink a radioactive solution so that then it will show up on the imaging. So they make those radioactive isotopes where they can see different things in your body using a cyclotron. And a lot of hospitals that do this will actually have a cyclotron in the hospital because these radioactive things, these solutions don't stay radioactive for long, so they have to make the radioactive material and then immediately give it to the patient. So they have to actually have cyclotrons in their building or very close to it. And cyclotrons, or at least this sort of equation, is actually how we were able to prove the existence of antimatter. So here is the discovery of the positron, which is the antiparticle of the electron. So it's charged Same magnitude as the electron, but positive. Same mass. Everything else is exactly the same as the electron, except it just has a positive charge. And what they do is they send particles into a chamber where they can track the movements of the particles. And then judging by, and this chamber has a magnetic field in it, and then judging by the direction that the particles spin in, they can tell its charge. By the radius, they can tell its mass to charge ratio, its velocity. So this is used a lot in modern physics, and this equation is also used a lot in like particle accelerators like CERN. You can see all of these little sort of like spiral things here are particles that get created, and then there's a magnetic field, and they spin in this magnetic field, and from their behavior in that magnetic field, we can learn a lot about what kind of particle it is. So we've discovered new particles this way, namely, like I said, the positron. And you might also think like, okay, well, who cares about antimatter? But actually, antimatter is still used in a lot of medical procedures today. For example, PET scans, which stands for positron emission tomography. That procedure actually uses positrons to image different parts of the body. So as I mentioned, the electron has an antiparticle, but all particles actually have antiparticles. And we don't really know why. If you've watched the movie or read the book, The Da Vinci Code, they have a matter, antimatter, like energy machine. So if matter and antimatter meet, they actually annihilate into just pure energy according to the equation E equals mc squared. So this is sort of one of those like science fiction, but maybe in the future it could be true, energy machines. And we don't really know why there's two copies of everything and why our universe is made up of matter as opposed to antimatter. There's no reason, there's no real justification that we have as to why everything that we see is made up of matter as opposed to antimatter. That was actually one thing that I studied while I was doing my PhD, was this matter-antimatter question, since our whole universe is made up of matter, and we don't know why that's the case. So antimatter was actually discovered by a physicist named Paul Dirac. So he was one of my favorite physicists, and it was actually just through this equation called the Dirac equation. So just this short, simple equation predicts the existence of antimatter, and that every particle has an antiparticle with equal and opposite charge, and everything else the same mass, everything else. And even Paul Dirac, when he first came up with this equation, he didn't even really believe it himself. He didn't really believe that what it was mathematically implying actually was reality, and it turned out that just the mathematical implications of this equation, however crazy they seemed at the time, were actually right. So this matter-antimatter question is one of like the biggest questions, one of the biggest unsolved problems in physics is why is our universe made up of matter as opposed to antimatter, and why is there that asymmetry? Why did the universe choose matter over antimatter? All right, so let's move on to now cyclotron frequency. So since our particles are moving in a cyclotron in uniform circular motion, that means that they're going to have a frequency, revolutions per second. So we can, again, think back to uniform circular motion and work out this frequency. So just to remind you, the radius is mv over qb. And now from uniform circular motion, we're going to be looking at the angular frequency. So that's the radians per second. And the angular frequency, which is given by lowercase omega, is v over r. So I'm going to plug in, where I see v, I'm going to plug in omega times r. So I'm going to plug in omega times r into this equation. And now I'm going to solve for omega. So I can see that my r's cancel, so the radius actually doesn't matter. And now I can solve for omega. So omega is going to be equal to qb over m. So this is going to be our cyclotron frequency. So it only depends on the particle's charge, the magnetic field, and the mass. And again, we're just going to take the magnitude here since we can't have a negative angular frequency. And the units of this are radians per second, as I mentioned. So omega is measured in radians per second. And if we wanted to just get the frequency, which we denote by f, Remember, F is equal to omega over 2 pi, and it's measured in just revolutions per second or hertz. So now let's do a simple example with this. So what magnetic field strength is required for electrons to move with frequency F equals 2,450 megahertz in a cyclotron? So we had our omega, let's just write all our formulas, was QB over the mass. And then remember, the frequency is omega over 2 pi. So let's replace omega with F times 2 pi, or 2 pi times F. So let's replace that right here. So we have 2 pi times F is equal to QB over M. And we are going to want to find the magnetic field strength. So we want to solve for B. So let's solve for B is equal to 2 pi F M over Q. So let's plug those numbers in. We have 2 pi. The frequency was 2450 megahertz, so that's 10 to the 6. And then the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And then the charge of an electron is 1.6 times 10 to the negative 19. So just plug all that into your calculator, and this becomes 0.0877 Tesla. So we'll talk about this a little bit more next time, but generally, just like sort of everything else, our Teslas are going to be usually much smaller. We're not really going to be looking at like 4, 5, 6 Tesla magnetic fields. Those are very, very strong. So they'll usually be smaller numbers like this. Okay, so this is just a basic equation of plugging these formulas in. Now let's move on to another problem with the cross product. All right, so here we have a proton with velocity given by this. So we've got some velocity in the x direction and some component in the z direction. Enters a region with magnetic field of 0.5 Tesla directed along the x-axis. So let's draw our axis like this. We have x, y, and then the z comes out like this. So our magnetic field is going in the x direction. We've got 0.5 Tesla. And we want to find the force on the proton and its acceleration as it enters the magnetic field, the radius of its path, and its angular speed. So since this proton is coming in with, it has some component in the x direction and some component in the z direction, it's going to be coming in sort of like in this plane here. So let's write our Lorentz Force Law. So we've got F is equal to QV cross B. So let's just look at our cross products first. So we have QV is, we have Vx, we've got some component in the x hat direction, no component of velocity in the y hat, and then we have a component in the z hat, and we're crossing that into a magnetic field that is only in the positive x hat. So we have that, I'll call that B in the positive x hat. So again, we can see that we have a component of our velocity in the x hat, and the component of our magnetic field is in the x hat. So these components, when you cross them into each other, is just going to give you 0. X cross x is 0. So only the z component of our magnetic field here will contribute to that circular path. Now, if you're not comfortable making sort of jumps like this, that's okay. If you want to, by hand do out the cross product every time, that's totally fine. I'll do it also when I write up the solution so that you can see that only the z component here actually matters. So we know now that we're going to have only our z component. We'll have Q Vz times B in the x direction. And now we're going to have z cross x hat. Now z hat cross x hat will just give us j hat, or y hat. So this will just be in the y hat direction. And now we can just plug our numbers in. Q is 1.6 times 10 to the negative 19. The x component of the velocity is 2 times 10 to the 5th. And the magnetic field is 0.5. So just multiply these out. Obviously, some of your 2's cancel here, and you're left with just 1.6 times 10 to the negative 14 newtons. So this is the force on our our proton here. So, okay, so this is our force. So we found its force. Now we want to find the acceleration. So for the acceleration, remember F equals ma. So to find the acceleration, all we have to do is divide the force by the mass. So we have our force was 1.6 times 10 to the negative 14 in the y hat direction. And this is going to be in the y hat as well. And then the mass of a proton is, I always forget, 1.6 times 10 to the negative 27. So you can just divide this out, and this comes out to 9.58 times 10 to the 12. Obviously, I'm being a little careless with my significant figures, but that's okay. And this is meters per second squared in the y hat. Okay, so this is our acceleration now. Remember, acceleration is a vector, so it has a direction. Okay, so this is our acceleration, and now you might notice here that our acceleration is actually very large. It's 10 to the 12, and you might think, well, that's bigger than the speed of light, and the speed of light, remember, is 3 times 10 to the 8. But remember, the speed of light is a velocity, so it's just in meters per second, so nothing can actually travel faster than 3 times 10 to the 8. But just because you have a big acceleration doesn't mean that your particle is actually traveling like at 10 to the 12 meters per second. It just means it's having a very, very fast acceleration. So it's actually okay to have an acceleration that looks like it's sort of bigger than the speed of light, because you're not actually going to be going the speed of light. Okay, now let's move on to, we found its acceleration. We want to find now the radius of its path once it gets into this magnetic field. So as the proton enters this field, as we saw, the z component of its velocity makes it move in that circle. So the z component is what's feeling the magnetic force and will make it move in that circular motion. But it still has a component in the x direction. So it'll actually keep traveling in the x direction because, as you can see, the velocity in the x direction here is unaffected by the magnetic field. So this particle will actually travel in a helix. So a helix sort of just looks like that. A helix is just sort of like a spring or like a coil. So we'll have some velocity and some displacement in the x direction, and then this velocity in the z direction will give it that spin. Okay, so we want to find the radius of its path. So the radius is mv over qb. But we have to be careful here because, like I said, it's only the velocity in the z direction that is feeling that magnetic force and thus contributing to its cyclotron and circular motion. So we actually only want to use the z component here, not the full velocity. So we're just going to actually use the z component of our velocity there, since the x component doesn't even know there's a magnetic field, basically. So we have the mass of an electron, which is, it's a proton, which is 1.67 times 10 to the negative 27. Its velocity in the z direction was 2 times 10 to the 5. The charge is 1.6 times 10 to the negative 19. And the magnetic field was 0.5 Tesla. Yeah. So we just plug all these things into our calculator and we get 4.18 times 10 to the negative 3 meters. So about a millimeter, 4 millimeters wide circle there. Okay. So now we found the radius that it's going to travel in, and now we want to find its angular speed. So the angular speed is omega. So the angular speed is given by QB over M. So we just have to plug these things in here, and we get Q is 1.6 times 10 to the negative 19, B is 0.5, and the mass, again, is 1.67 times 10 to the negative 27. So this comes out to 4.79 times 10 to the 7. Remember, this is radians per second since it's angular speed. All right, so I just want to, that's all the new material for today, but I'm just going to quickly go over circular motion since I know that's easy to forget. So let's just quickly go over circular motion, uniform circular motion. Just a couple of the main equations. So obviously when we're in uniform circular motion, that means that we're moving in a circle. Our velocity is tangent to the circle. So the velocity is tangent, and there's an acceleration directed inward, which is keeping us moving in that circle. And the speed that we're moving around that circle is constant. So the magnitude of this velocity vector, even though the velocity vector is changing direction, the magnitude of it is constant. And since the velocity vector is changing direction, that's how we know there's some acceleration going on. Even though our speed is not changing, our direction is. Okay, so like I said, so the acceleration is given by v squared over r. I'll use little r. So the acceleration is directed inward, and it's just the velocity squared divided by the radius. And this is obviously measured in meters per second squared. Then our angular velocity is how many radians per second we're moving in. Angular velocity, like I said, is given by omega, and it's given by v over r. We can also write this as 2 pi times the frequency, and this is measured in radians per second. And then our frequency, as I mentioned, is you can write it as omega over 2 pi, and it's given by revolutions per second, or hertz. And then don't forget also our period. So the period is how many seconds it takes to trace out one revolution, and it's the inverse of frequency. So a period is 1 over frequency, and it's just measured in seconds. So this also means that we can write our angular velocity as 2 pi over the period. And that also means that we can write our frequency here also as just 1 over the period. So those are the basic things for circular motion. All right, so that's it for today. Next time we will finish up chapter 27, and I will see you guys then.